Previously in class, we talked about static electricity, which is electrical charge that's held in one place. But that doesn't describe the electricity that we're most familiar with on a daily basis, the electricity that runs all our devices, our TVs, our phones, everything. To do that, you have to have electricity constantly flowing from one place to another. And that's called current. So we're going to talk about electric current in this video. That's what these notes are about. The definition of an electric current is simply the flow of electric charge by movement of electrons. You know that the electrons are what is involved in electricity, and when they move from one place to another, that's defined as a current, as an electric current. Electrons will spontaneously flow from areas of high negative charge to areas of high positive charge. What that means is that, let's imagine I have these two objects. One has a charge of negative 10 microcoulombs, the other is neutral. The question is, if I put these two objects together, I bring them into contact and allow conduction to occur, what direction will the electrons flow? Hopefully you know that electrons will flow spontaneously this direction. The word spontaneously is what we just used in your notes. The word spontaneously, remember, means that we don't have to apply energy to make this happen. This happens automatically, and we use that same term when we talked about the second law of thermodynamics in relationship to a heat engine. Because if we have a high temperature reservoir and a low temperature reservoir, we said that the second law of thermodynamics states that heat energy will spontaneously flow from the hot to the cold every single time. It's a spontaneous process. We don't have to put energy into it to make it happen. So these electrons spontaneously flow from areas of high negative to high positive. Now, one modification is that you'll see this is a neutral object. It's not a highly positive object, but the point is that it's less negative than this is. We've got a lot of electrons that are kind of piled up over here. They don't want to be next to each other. They don't want to be in close proximity because objects that have the same charge repel each other. And so that's where this comes from, this spontaneous movement. They would rather go away and move somewhere else where there aren't as great of an electron concentration. So that's the idea behind spontaneous movement. The flow stops when the potential difference is equal. You need to understand what this term potential difference means. Potential difference can be thought of as like potential energy. As I said, there's a lot of energy bound up here because of the proximities of these electrons. These electrons over here, there are some here, but they're not as closely bound together. There's not as much energy here because they're not repelling each other quite as hard. As you know, with electrostatic force, the closer the electrons are, the greater the force. So there's a lot more energy that's bound up here. There's a lot more potential energy, has the potential to do work. And because there's two different charges, there is a difference in potential energy. You have a potential difference. As long as there are different amounts of potential energy in these places, electrons will flow from the high potential to the low potential. And this happens until the two objects equal out, until their charge is equal. This is conduction. At this point, the potential energy is exactly equal. There's some potential energy here, but it's the same in this place as it is in this place. So there's no reason for electrons to flow spontaneously from one place to another. They might move back and forth, but there's not going to be one specific direction for them to go. So when the potential difference is equal, the flow is going to stop. This is still static electricity, though, that we're talking about. Static electricity means we've collected charges and we can move them from one place to another, but that movement stops when the potential difference is equal. This kind of movement cannot run a device, at least not for very long. In order to run a device, we have to find a way to get these electrons to continue moving, to continue to flow. And you know that flow is electric current. In order to continue that flow, to keep the current flowing, there's got to be something there that keeps it flowing. It's called a charge pump. We can call it a charge pump, but another name for it, the name that you're more familiar with, is simply a battery. And when you break a battery down to its most simple form, the really simple definition of a battery is simply that it is a device that converts chemical energy to electrical energy. That's all it really does. And when we put it in those terms, it really brings us back to this equation. Do you remember a while ago we talked about the fact that work is change in energy? And I told you that this equation is really It's the center of this physics class. It's the most important thing that we'll talk about, because anytime we have a change in energy, work is being done, and really everything that we've talked about is all about energy changing, either changing amounts or changing forms. And so when we talk about batteries that convert chemical energy into electrical energy, all we're doing there is changing energy, therefore work is being done. When energy is changing, work is being done. So when you think about the battery in those terms, it's really no different from any other device that converts electrical energy, any form of energy to any other form of energy, such as a photovoltaic cell, also known as a solar cell, that converts light energy or solar energy into electrical energy. That's what the solar cell on a solar operated calculator does. A generator, you can have a generator which converts kinetic energy into electrical energy, and in the form of kinetic energy from water, like from a waterfall with a hydroelectric plant, steam kinetic energy, wind kinetic energy with a wind generator. There's also those really cool flashlights that are run off of a hand crank, that you crank the handle or you can shake it, and it's the same thing. It's converting kinetic energy to electrical energy. All of these devices are simply devices that have charge pumps, but the battery is the one that we're going to focus on today. So this is the picture of the battery that's in your notes, and it's important that you understand how a battery works, and that's what I'm going to go through here. This is the schematic drawing of a battery. Not every battery looks exactly like this, but every battery will have these same components to it. There are always two terminals made of some conducting material, and this gray matter that's in here is some sort of insulating material, an insulator. And remember that insulators simply prevent the flow of electric charge, and that's going to be important in just a minute. Remember that this battery converts chemical energy to electrical energy, and that chemical energy comes from a chemical reaction that happens inside of here. There's a chemical reaction that is constantly occurring 24/7 in every battery. And what that chemical reaction does is it continuously pulls electrons off of the positive terminal and deposits them onto this negative terminal. In other words, it's concentrating electrons preferentially over this way. And that's significant because, remember, if we're concentrating electrons, remember this drawing we did, these electrons don't want to be close together. They're exerting a force on each other, and they would rather be on the other side. They want to be on the positive terminal. So this chemical reaction is doing work. Work is being done on the electrons because it is fighting the electrostatic force. It is going against the force that wants to pull these electrons back over this way. This work done on the electrons versus work done by the electrons is an important point. Remember when I talked about thermodynamics, I talked about the difference between work done on a system and work done by the system. When work is done on the system, remember I talked about a bike pump, and when you pump a bike pump quite a few times, remember I talked about, here's a bike pump here, when you pump it up and down 50 times, the temperature of this pump increases. Well, that means that the energy of the pump has also increased. The reason why the energy of this system increased is because you took energy, here's you up here with your hands on it, the energy came from your own body and went into the pump. The energy came from outside the system. That is work done on the system. Well, that's what this chemical reaction is doing on the electrons. This chemical reaction is taking the chemical energy contained in the chemicals. It's doing work on the electrons and increasing the energy of the electrons. That's what it does when it deposits the electrons over here on this negative terminal. They're deposited here, they're highly concentrated, and there's a lot of energy, high potential energy here, because they would rather be on this side. If we let them, they will spontaneously flow this way. As of right now, let's imagine this wire is not here. They cannot flow this way because, remember, this is an insulating material. If we don't connect the two, they're going to stay on this side. But now we're going to connect the two with a wire. What that does is it provides a path for the electrons to flow. If given a path, the electrons will, remember, spontaneously flow from a high potential to a low potential, from high negative to low negative. So the electrons run through this wire. This is a circuit. This is a current. The electrons run through here. This is a spontaneous process. And remember, I mentioned this before. This spontaneous process we talked about, this is the second law of thermodynamics again. Remember, we talked about it in relation to heat engines. With the heat engine, what we did is we took advantage of this spontaneous process to get work out of it, which created some kinetic energy for us. And that was a good thing. Well, it's going to be the same thing here. What we're doing is we're going to take advantage of this spontaneous flow of electrons, and we're going to get some work done out of it. Work is done by the electrons at this point. The work is done on the electrons here, which means the energy is transferred to the electrons. And now the electrons have energy, and they themselves are going to do work as they run through this wire. This work done by the electrons, remember the image I gave you in class is you going out and running a mile. That's kind of a weird looking runner, but you get the point. This is a runner running a mile. This is you going out on the track and running a mile. And remember when I said that you did that, this is work done by the system. You are the system in this case. In that case, the internal energy of the system goes down. You, at the end of the mile, have less energy than you had before. And it's no different with these electrons. When the electrons do work, what you need to draw up here is that this is a light bulb. The electrons are doing work up here. They have energy, and they are giving up that energy to this light bulb. They're running through the light bulb or the microwave or the TV or whatever it is, and they're giving up that electrical energy. They're converting that electrical energy to light energy or heat energy or sound energy or whatever other energy that is being used. That work is being done by the electrons. Their energy decreases, and really by the time you get it back around, their energy is just about gone. They have no more energy by the time they get back around to this low potential side. And then when they get back here, remember the chemical reaction is constantly occurring, constantly pulling electrons off of the positive terminal over to the negative terminal. This constantly happens. And now this brings us to the next question. Well, what does it mean when we have a dead battery? What does it mean when you go out to your car and you say, well, my battery's dead? Well, what it means is that this chemical reaction can no longer occur. Hopefully you remember when you took chemistry that there is no chemical reaction that can occur forever, and it's the same with this one. Eventually the reagents get used up, and this reaction can no longer pull electrons from one side to the other. When that happens, it doesn't mean that there are no charges in there. It doesn't mean that there are no more electrons. It means the electrons are simply evenly distributed between these two places. And remember what we said before, if the electrons are evenly distributed, there's no more reason for the electrons to flow. And it's the same here. Your battery is dead when there's no reason for electrons to spontaneously flow from one place to another because you don't have negative charges piling up in one side. That's what it means when your battery is dead. All right, so now that you know a little bit about the battery, I want you to take a minute and see if you can fill in the blanks with these three questions. Pause the video. All right, if you pause the video, hopefully you can figure out, answer these questions. Which side of the battery does the electron want to be on? Well, the electron would rather be on the positive side if it could quote-unquote choose. Not like the electron has a choice in the matter, but electrons are attracted to positive charges, so it would rather be over here. That's what naturally would occur. Since the electron doesn't want to be on the negative side, it takes work to get it there. The work done on the electrons is done by the chemical reaction, which takes the electrons over here. The potential difference, which is the same thing as voltage, is the amount of work done on the electrons as they are moved. Electrons, when work is done on electrons, they're moved from the positive terminal to the negative terminal. This work is done by the chemical reaction. So voltage is the amount of potential energy that's piled up over here. The bigger the chemical reaction, the more electrons we can pile up over here, which means the greater the difference in potential, which means the greater the voltage. If these terminals are connected by a conducting wire, the electrons are going to spontaneously flow through a conductor from the high potential terminal to the low potential terminal. That's what happens spontaneous. So this process up here is spontaneous, flowing from high to low potential. This process down here is not spontaneous. We have to do work on the electrons to get this to happen. This flow of electrons is an electric current. As the currents move through the wire, they are able to do work, like run a motor or a flashlight or whatever else you're talking about. So that's the basics of a battery.